All right, let's jump right into this explainer. Today, we're building up your expert CISSP exam mindset, specifically focusing on Domain 8 and Domain 3 topics. Think of us as your lead instructional design team. We're going to give you a highly structured, comprehensive breakdown of software development security and database security. If you're gearing up for the exam, you are exactly where you need to be. Here's our roadmap for today. We're going to cover secure coding in Toolsets, development lifecycle models, security and system operations, database architecture and concepts, database security threats, and wrap things up with knowledge-based AI systems. We'll take these complex engineering concepts and distill them into the precise takeaways you need. Let's kick things off with Section 1, Secure Coding and Toolsets. We have to start by looking at the fundamental tools and languages developers use to build custom solutions, because, well, that's where vulnerabilities first emerge. It is always easier to build security into a system right from the start, rather than trying to bolt it on later. Now, take a look at the clear distinction here between compiled and interpreted languages, and the unique security risks that each one presents. Compiled code, think C or Java, uses a compiler to convert source code into a binary executable. This makes it super hard for end users to reverse engineer or manipulate. But on the flip side, it makes it a prime hiding spot for malicious developers to embed backdoors that completely escape detection. Interpreted code, like Python or R, is a different story. The actual source code is distributed. So while you don't have to worry as much about hidden developer backdoors, since literally anyone can view the original instructions, it is incredibly prone to being modified and manipulated by anyone who gets their hands on it. To keep all this code organized, developers rely heavily on integrated development environments, or IDEs. IDEs centralize programming efforts. They give developers a single cohesive environment where they can seamlessly write, test, and debug code. That is absolutely vital for maintaining secure coding practices, long before the software ever reaches a production environment. When you're dealing with object-oriented programming, you've got to remember this critical distinction. Cohesion describes the strength of the relationship between the purposes of methods within the exact same class. When all the methods have similar purposes, you have high cohesion. That's fantastic software design. Coupling, on the other hand, refers to the level of interaction between completely different objects. Lower coupling means less interaction. It makes those objects more independent, easier to troubleshoot, and ultimately way more secure. So, here's the crucial point. You will almost certainly see a question testing your ability to distinguish between these two concepts on the exam. Lock this ideal state into your memory right now. High cohesion and low coupling represent the absolute pinnacle of secure software design. Keep that in your back pocket. All right, moving right along to Section 2, Development Lifecycle Models. Let's see how these coding concepts build into broader, formalized lifecycle management processes that actually embed security into product development. This is the Software Capability Maturity Model, or SWCMM. This framework is all about evaluating organizational process maturity. It tracks an evolutionary path. It starts at level 1, the initial phase. This is where you usually find that chaotic, ad hoc, duct tape and chicken wire style of coding. But as an organization matures, it progresses through repeatable and defined stages, eventually hitting level 5, the optimizing phase. At level 5, you've got sophisticated processes focused entirely on continuous improvement and proactive defect prevention. It's night and day. Now let's contrast those rigid maturity models with Agile development. The Agile philosophy completely tosses out the rigid, highly documented models of the past. Instead, methodologies like Scrum rely on daily meetings and short sprints of activity, usually just 1 to 4 weeks. The whole goal is to prioritize working software, flexible customer collaboration, and a rapid response to change over just blindly following a plan. Here's a major CISSP exam mindset note for you. Do not fall for a test trap that tries to confuse these frameworks. Just remember, SWCMM is an evaluation of an organization's maturity level, while Agile is a flexible, iterative philosophy for how the actual development work gets done. They are fundamentally different. Section 3, Security in System Operations. Once that software is actually built, it has to be operated securely, and that brings us to handling system failures and managing ongoing modifications. Let's pause for a second and consider a classic scenario-based thought experiment. When the unexpected happens, how should the application respond to protect resources? Should it fail open or should it fail closed? The answer is almost always fail secure or fail closed. This prioritizes confidentiality and integrity by simply disabling the system, rather than bypassing controls in some permissive fail-open state. Just think of the infamous Windows blue screen of death. It is literally a stop error. The OS realizes the environment is no longer trustworthy, so rather than allowing a process to bypass an access check, it shuts the whole thing down. That is a textbook fail-secure response. Any updates after a failure, or honestly even just regular maintenance, absolutely must go through a strict change management process. Step 1, request control, prioritizes the task with a cost-benefit analysis. Then, change control allows developers to recreate and analyze a solution. But release control, that is the critical security gateway. You have to ensure that any code inserted as a programming aid during the change process, things like debugging code or backdoors, is completely removed before releasing that new software to production. Section 4, Database Architecture and Concepts. We're shifting gears a bit into Domain 3 territory now to explore exactly how we store and protect the incredibly valuable data our secure applications are generating.
Every single relational database transaction has to adhere to the ACID model. Think of a financial transfer between two bank accounts. The transaction must be atomic, meaning it's an all-or-nothing deal. If the database crashes right after subtracting funds from account A, but before adding them to account B, the entire transaction rolls back so that money doesn't just disappear into thin air. It also has to maintain consistency with database rules, operate in isolation from other transactions, and possess durability. Durability just means that once a transaction is committed, it's preserved permanently via backups and logs.
You also really need to know how database tables relate to one another. A primary key is a unique identifier for a row within a single table. Think of something like a customer ID. But the foreign key is what links back to a primary key in another table. For example, an orders table might have a foreign key that points back to the customer ID. It enforces the relationship between the two.
So the crucial exam mindset point here is referential integrity. Referential integrity ensures that no record contains a reference to a non-existent primary key. A super common exam trap will try to confuse alternate keys with foreign keys, so lock this fact in right now. Referential integrity is strictly the domain of the foreign key. Section 5, Database Security Threats. Look, even with absolutely perfect architecture and rock-solid referential integrity, data is still vulnerable to unique threats that can totally bypass standard access controls. Let's look at two of the most critical ones. It is incredibly vital to understand the distinction between these two threats because they get confused all the time. Aggregation uses raw math and SQL to combine data. Imagine a low-level clerk counting hundreds of unclassified individual transfer requests just to calculate highly classified total troop levels at a military base. Inference, however, relies entirely on human deductive capacity. It's like an accounting clerk realizing someone was hired yesterday, pulling the total company payroll for yesterday and today, and deducing that one specific person's exact salary just by subtracting the difference. Make sense?
To defeat those sneaky inference attacks, military databases use a fascinating concept called polyinstantiation. Imagine a database tracking naval ships. A ship called the USS Up to No Good goes on a top-secret mission. If a user with only a secret clearance suddenly can't query that ship's location, they're instantly going to infer something is up. Polyinstantiation fixes this by creating two records with the exact same primary key. So the user with a secret clearance queries the database and sees a decoy routine patrol location, while a top-secret user queries the exact same key and gets the real classified coordinates. Pretty brilliant, right? All right, moving to Section 6, Knowledge-Based AI Systems. Let's head into our final section and see how all this builds into advanced systems that can actually automate complex security analysis.
We're increasingly relying on AI to rapidly make consistent decisions on massive amounts of audit trail data. You need to know the distinctions between these systems. First, expert systems use codified, human-provided if-then rules processed through an inference engine. Next, machine learning scales that up. Supervised ML uses labeled data. Essentially, we give the computer the correct answers to train it. Unsupervised ML uses unlabeled data, forcing the algorithm to independently group data and find anomalies all on its own. And finally, neural networks, or deep learning, simulate actual human biological reasoning through massive layered chains of computational units.
Which leaves us with a really critical question for your ongoing CSSP journey, and honestly, your entire career. As these machine learning models and neural networks increasingly take over our software development and database analysis, are we actually prepared to secure the very algorithms that secure us? How will the definition of due diligence evolve? It's something to think about. Thank you so much for joining me for this explainer. Keep that exam mindset strong, and I'll catch you in the next one.